In this lecture, we are going to discuss a formalism which is known as isotopic spin formalism. Actually, the charge independence and charge symmetry, and at the same time the almost equality of masses of neutron and proton. These facts actually give suggestion that the neutron and proton are same particle in two different charge states. So mathematically it is possible to treat neutron and proton on an equal footing, and in fact this is conveniently done by introducing a mathematical three-dimensional space which is called charge space. Actually, this three-dimensional charge space in which we deal with the neutron and proton on same footing is known as isotopic spin space or isospin space, or you can simply say isospace. In fact, in this isospace, the neutron and proton are described by an isotopic spanner or isospanner field. In fact, there are two isospanner components corresponding to the two charge states of the nucleon. And you know the ordinary spin has also two states. You know there are two states of ordinary spin, up and down states. So in just like that, the formal development of the isospanner algebra is exactly same as that of the ordinary spin. And on the line of the ordinary spin, we actually develop the algebra of isospanner. So see here, you have definitely taken course in quantum mechanics on the spin and particularly the Pauli spin matrices. So for ordinary spin, you know the spin angular momentum S is given as H cross over 2 sigma. Actually this sigma is Pauli spin matrices, and the Z component of S is, if we write the Z component by the symbol S3, or you may write it as SZ. So what is this SZ? We know you have studied in the topic spin in quantum mechanics. This SZ is actually equal to plus minus H cross over 2. In fact, these are the general result which we study in case of the common spin. As I have told you, in the field of charge space, or you can say the isotopic spin space or isospin space or simply isospace, as the neutron and proton are treated on common footing, so these two particles has a common name. They are called in fact nucleon, and this nucleon is defined by a isospin vector. Just like that, here we define a particle, a quantum particle like electron or proton or neutron by this spin vector. In similar way, in isospace we define the nucleon actually with a vector that is called a vector, or you may say a quantity just analogous to the spin angular momentum. In this isospin space, we define the isospin of the nucleon. And how it is defined? This is actually defined on the line of this definition of ordinary spin. So, a nucleon is a particle with isospin. This is denoted by the symbol T, and this is equal to 1 over 2 tau. Say this is equation A. In fact, here you can see that this T is analogous to S. T is equivalent or analogous to S. And this tau is analogous or equivalent to this polyspin matrix sigma. And just like the Z component of the spin vector S, we also define the Z component of this isospin T. So, Z component of T in isospace, or you may say isospin space, are given as. In fact, this Z component is denoted by the symbol T3, or you can say in fact TZ, and this is given as 1 over 2 tau 3. 1 over 2 tau 3. And this is actually equal to plus minus half. In fact, this tau 3 has the value plus half for proton, and this T3 has the value, not tau 3, but T3 has the value minus half for neutron. Although just it is a convention, we may take the just opposite convention. So actually we can say that this T3 is equal to half for proton, and it is equal to minus half for neutron. Although I have told you that we can take just the opposite convention, that is, we can take T3 equal to minus half for proton and plus half for neutron. It may be taken, but this is the most popular convention in which we take the Z component of isospin vector T, which is denoted by T3, as equal to half for proton and minus half for neutron. And actually from this value you can see here that as T3 is equal to 1 over 2 tau 3, and from this we can see this is equal to plus minus half, and so what will be this tau 3? tau 3 will be actually equal to plus minus 1. And you can see in accordance with this convention that this tau 3 is equal to plus 1 for proton and this tau 3 will be minus 1 for neutron. Although we will express this tau 3 in fact as a matrix. In fact this tau has actually 3 components and all the 3 components are just analogous to the 3 Polish spin matrices. So you can say just like the 3 components of Pauli spin matrices denoted by the symbol sigma, the 3 components of isospin matrix tau are. In just like the 3 components of Pauli spin matrices, we define the 3 components of the isospin matrix tau. And how it is defined? This is in fact tau 1 equal to G matrix 0 1 1 0. This is just a 2 by 2 square matrix. Its another component tau 2, which is in fact tau y. This is 0 minus I and 0. And its third component, that is Z component tau 3, is 1 0 0 minus 1. These are the 3 components of the isospin matrix tau. And from these values, in fact, we can express the wave function of the proton or neutron in isospace. So, wave functions of the proton and neutron in the isospace are given as. How it is defined? The wave function for proton is written eta p, and it means this is eta, and you know for this eta T3 is equal to plus half in accordance with our convention, and this is given by a column matrix 1 0. Say this is 3a, and the wave function of the neutron, this is eta n, and this is eta T3 equal to what? This is minus half for neutron in accordance with our convention, and this is given by the column matrix 0 1. This is 3b. And from these results you can see that we can see or we can write the eigenvalue equation for these wave functions. So we can write T3. You know this T3 is just like an operator, and in fact the eigenvalue of this T3 is 1 by 2 for proton and 1 by 2 for neutron. So we can write the eigenvalue equation T3 eta p is equal to actually 1 by 2 eta p, and T3 eta n, this will be equal to minus half eta n. You can see this is nothing but eigenvalue equation, and here 1 by 2 is the eigenvalue of T3 for proton, and minus half is the eigenvalue of T3 for neutron. So these are simply the eigenvalue equation for this operator T3. Now we introduce a very important operator in this regard, and that very important operator is known as charge operator, and we will denote it by the symbol capital Q. So here I am just introducing an operator Q, and this Q is known as what? This is known as charge operator. Charge operator. Actually, the eigenvalue of this charge operator Q is +1 for the proton state, and its eigenvalue is 0 for the charge for the neutron charge state. So you can write eigenvalue of Q for proton state is equal to +1, and eigenvalue of this operator Q, that is charge operator, for the neutron state this is equal to 0. And so we can define this operator Q in a particular manner. So we can define Q as, how we can define it? You can, first of all, I am writing its definition and then you can check it. So this Q is defined as 1 over 2 1 plus tau 3. 1 over 2 1 plus tau 3. And in matrix form, this Q can be written as 1 0 0 0. You can understand why we have defined this operator Q in matrix form like this, and then we can verify this result too. So how we can verify it? Let us see. If we want to find the eigenvalue of this operator, so what will be the eigenvalue? If we consider that lambda is the eigenvalue of this matrix, then if I am just writing it in very short, I hope you have already studied the eigenvalue and eigenvector of matrix. So if lambda is the eigenvalue, what will be the characteristic equation? This will be simply lambda minus 1 into lambda minus 0 equal to 0. See these diagonal elements, and this is simply lambda into lambda minus 1 equal to 0, and this implies lambda is 0 and lambda is 1. So you can see that this operator Q has an eigenvalue 0. This is in fact for the neutron state, and the another eigenvalue is +1, and that is for proton state. So if we represent this operator Q in this form, in this matrix, in the form of this matrix, then this eigenvalues are satisfied, and so we can express this operator in matrix form like this. And how we can test this result? You can test it. So see this result and find the value of Q from here. This is 1 over 2 into 1 plus tau 3. See here, I have just mentioned the value of tau 3 in this matrix form, or you can take the value of tau 3 like this, that is +1 for proton and -1 for neutron. So if we will take the value of this tau 3 plus -1, so what will be the value of Q? If we will take +1 its value, that is tau 3's value, then the result will be 1, and if we will take -1 for tau 3, this will be 0. So you see that the eigenvalue of the operator Q is again satisfied by this expression. So we can define the operator Q like this or in matrix form like this. I hope you have understand why these two formulas are used to define this charge operator Q. Now, in terms of the wave function of the neutron and proton, now we can write the eigenvalue equation of this operator Q. So what will be the eigenvalue equation? So you can write, so eigenvalue equation of Q are Q eta p. This is in fact a wave function for proton. You know, the in case of eigenvalue equation, here we should write the eigenvalue, and you know for proton the eigenvalue of Q is what? Actually its eigenvalue is 1, and so this will be simply eta p. And Q eta n, we know the eigenvalue of this operator Q for neutron is 0, and so 0 times eta n, that will be simply 0. And these are the eigenvalue equation for this operator Q, and you can say this is equation number 4. You can check this this eigenvalue equation by in the matrix form too. I have just defined the matrices Q and matrix eta p. So you can, in an alternative way, you can check this result. So what will be this Q eta p? See here. As you know, the matrix Q is defined in this form 1 0 0 0. So you can write this is 1 0 0 0, and you have seen that the wave function for the proton eta p is defined as see here, the wave function for the proton I have defined somewhere. You can see this is definition. Eta P is column a column matrix 1 0, and eta n is a column matrix 0 1. So put this matrix here. This will be 1 0, and let us multiply it. 1 times 1, that will be 1, 0 times 0, that will be 0, and 0 times 1, that will be 0, and 0 times 0, that will be 0. And so this is simply 1 0, and you know this column matrix is what? This is eta P. In similar manner, you can test that this Q eta n will be equal to 0. I am leaving it for your exercise. I have just tested this. So in these two ways, you can understand the eigenvalue equation for the operator Q, which is actually charge operator. Now here we also define two very important operators, which are in fact just analogous to raising and lowering operator. You have studied in quantum mechanics in angular momentum, raising and lowering operator, and in case of harmonic oscillator too. And these raising and lowering operators, in analogous to those raising and lowering operators, here we define two operators which are just analogous to the raising and lowering operator. In fact, these operators has a meaning that to increase or decrease charge of the nucleon by 1 unit. In fact, let us define the operators tau plus and tau minus. In fact, this tau plus operator raises charge of a nucleon by 1 unit. And this tau minus, this actually decreases, or you may say lowers, charge of a nucleon by 1 unit. Now, these operators tau plus and tau minus are defined in a particular manner. In fact, tau plus is defined as 1 over 2 tau 1 plus I tau 2. And the lowering operator tau minus, this is defined as 1 over 2 tau 1 minus I tau 2. And in matrix form, you can find the values of these two operators, and you can see. So this tau plus will be actually equal to 1 over 2, and see the matrix tau 1 is equal to what? You can see this tau 1 is actually equal to a square matrix 0 1 1 0. Just now you have seen it. And plus I, and what is the matrix tau 2? This is in fact 0 minus I I 0. You can simplify it. This is simply 1 over 2 This is 0, 1, 1, 0 plus. This will be 0 I times I square, that is minus 1, and here is minus, so this will be plus 1, and this is I square, that is minus 1, and this is 0. And what will be this? This is 1 over 2. 0 plus 0 is 0, 1 plus 1 is 2, 1 minus 1 is 0, and 0 plus 0 is 0. And so what will be this? You can see this top plus operator will be in fact matrix 0, 1, 0, 0. This is the matrix form of this operator. And in similar manner, you can find this matrix tau minus. You can do it yourself. I am just writing its value in the similar manner. Tau minus is equal to what? This will be actually 0, 0, 1, 0. So in matrix form, we have defined these raising and lowering matrices or operators. So from these properties of the tau plus operator and the tau minus operator, you can easily check. So I am first of all writing the different eigenvalue equation, and then I will test only one, and the remaining should be tested by you yourself. So we will have tau plus eta p. You can see this will be equal to 0. The another important equation will be tau minus eta p. This will be eta n, and tau plus eta n, this will be equal to eta p, and tau minus eta n, this will be equal to 0. And say this is equation 5. Actually, we can explain these results in two ways. First of all, you can see that this is a raising operator, and when it is operated on the eigen function or wave function of proton, it will raise the charge by 1 unit. But you can see, as there is no nucleon with plus charge, plus 2 charge, so it means in fact there will be no such nucleon, and so this is 0. And here when tau minus operates on the wave function of proton, it lowers the charge of the proton by 1 unit, and when charge of proton, which is in fact plus 1, is lowered by 1, it will become in fact 0, and 0 means the neutron particle will be obtained, and so the wave function is for the neutron. This is just a logical explanation, but in matrix form we can test any of these results. So let us test only first of all first one, and remaining I would like to tell you to test yourself. So let us take tau plus eta p will be what? In fact, I have just defined the operator tau plus. This is, see here, this is matrix 0, 1, 0, 0. So you can write matrix 0, 1, 0, 0. And eta p, you know the wave function of proton is the column matrix 1, 0. See here, This is in fact 0 1 0 0, and the eta p is 1 0. So let us multiply it. This is 0 times 1, that is 0, 1 times 0, that is 0, and 0 times 1 0, 0 times 0 0, and so this is simply a 0 0 matrix, and this is actually 0. You can test it. For your convenience, I am just testing one more. Let us take eta minus eta p. What will be this? Eta minus, as you have seen here, this matrix is 0 0 1 0. This is in fact 0 0 1 0, and eta p, this is 1 0, multiply it. In fact, this is 0 times 1, that is 0, plus 0 times 0, that is 0, 1 times 1, that is 1, and 0 times 0, that is 0. So this is matrix 0 1, and you know what is this? Actually this is eta of n. So we can write this tau minus eta p is equal to eta n. So these are the operators which can change the charge state of the nucleon. Charge state of the nucleon. And these are just analogous to the raising and lowering operators, you can say. Now we will see the two-nucleon wave function in isospin space. Two-nucleon wave function in isospin space. In fact, if we want to define the total isospin of two nucleons, let us say nucleon number 1 and nucleon number 2, then how it will be defined? Actually, the total isospin of a two-nucleon system is defined as the vector sum of the isospin of the first nucleon and the second nucleon. So the total isospin which is denoted by vector T, capital T, of two nucleons, 1 and 2, is defined as, how it is defined? In fact, it is defined as T is equal to T of 1 plus T of nucleon 2. And what will be the equation number? Actually this is equation 6, and say this is 6a. In fact, the value of this total isospin are in fact 0 and 1, where T is equal to 0 or 1. In fact, when it is 0, T equal to 0 implies actually the spin states of the two nucleons are actually anti-parallel. That is, spins are not aligned. and this T is equal to 1, this implies the spin states is that of parallel spin. So this total isospin has two values, one is 0 and another is 1. And we know if we want to write the wave function, then we can write the wave function by the use of CG coefficient, because here there is just a combination of angular momenta. So in terms of CG coefficients, we can write the wave function of t and its z component. As you know, the two operators which commute has a same set of eigenfunctions. So this t and its z component actually commutes, and so they have same set of eigenfunctions and our wave function, and we can write the wave function for t and its z component in similar manner. So you can write the two-nucleon wave function, two-nucleon wave function, which is denoted by eta 1 by 2 t mt, and this is the two-nucleon wave function, and this is represented like this, and actually which is an eigenfunction of t and t3. T3 means z component of t, is obtained by using CG coefficients. I hope you have studied CG determination or evaluation of CG coefficient in the topic angular momentum in quantum mechanics. So you must have acquainted from it, and you can write that the eigenfunction of t and t3 can be found by the use of CG coefficients, and how we can write it. So we can write it eta 1 over 2 t mt, and this is actually equal to summation over mt dashed, and here this m capital T is actually equal to mt plus mt dashed, and this is bracket 1 over 2 mt dashed t mt into eta of 1 mt, eta of 2, this is for nucleon 2, mt dashed. This will be actually equation number what? This is equation say 6b, and you can say this is equation 7. Actually here this empty and empty dash has two values, that is plus minus 1. So empty and empty dash take the values plus minus half. And from this equation 7, now we can actually find the isospin singlet state and the isospin triplet state. That is the wave function for the isospin singlet state and isospin triplet state. We can easily write it. So from equation 7, we can write the wave function for isospin singlet state and triplet state. So first of all, I would like to write the wave function for the isospin singlet state. Isospin singlet state. It is denoted by eta 0, 0, and actually this will be eta 1 by 2, 1 by 2, 0, 0. In fact, empty and T and empty are in fact 0, 0. These are in fact T and empty. And so, and it is actually equal to 1 over root 2 eta 1 for proton, eta 2 for neutron, and minus eta 1 for neutron into eta 2 for proton. Say this is equation 8. This is the wave function for isospin singlet state. Now we can see from this result that the isospin singlet state defined in this equation 8 is actually antisymmetric in nucleon 1 and in nucleon 2. Why we say that it is antisymmetric? If we will actually interchange 1 and 2, you can see that the sign of this wave function will be just reversed. If you will put here n and here p, and so the sign will be just reversed. So this result implies that the isospin singlet state is antisymmetric in nucleon 1 and 2. Nucleon 1 and 2. Now we will write the wave function corresponding to the isospin triplet state. Isospin triplet state. The three states are denoted by the symbols eta 11, eta 10 and eta 1 minus 1. So first of all, we will write the wave function eta 11. This is in fact eta 1 over 2, 1 over 2, 1, 1. And this is equal to eta 1 p and eta 2 p. Say this is 9a. The another state is 10 state, and this is eta 1 over 2, 1 over 2, 1 0, and this is equal to 1 over root 2 eta 1 p eta 2 n plus eta 1 n eta 2 p. Eta 2p. This is 9b. Now the third state is 1 minus 1 state. This is 1 minus 1, and this is eta 1 over 2, 1 over 2, 1 minus 1, and this equal to eta 1 n and eta 2 p. So you can see the form of the wave function defined in equations from 9a to 9c. And when we will in fact interchange the nucleon, that is the nucleon 1 becomes nucleon 2, or you can say that 1 becomes 2 and 2 becomes 1. In that condition, there is no change in sign of these wave functions. Sign of the wave function will remain same. And if sign of the wave functions remain same, we know the wave function is actually in that case symmetric. So you can see that the isospin triplet states equations 9a to 9c are symmetric in nucleons 1 and 2. So this was all about the isospin formalism, and now we will actually deal with some new concept in the forthcoming lecture, and that is also a most important concept, that is called the scattering problem. In fact, nucleon scattering is the most important problem of the nuclear force, because we know so many clues, so many properties of the nuclear force from nucleon scattering experiment. So in the forthcoming lecture, we will discuss nucleon scattering.